In this video, we're going to look at functions and loops. Functions and loops are both a little bit more advanced, but if you find yourself doing repeated processes while you're analyzing data, they can be really useful. So we're going to start out by looking at functions. So as we've seen in this course, writing a script is really useful, but often there's going to be some task, calculation, or several lines of code that you wish to repeat over and over again, but just with different values or maybe with a different data set. And so for cases like this, it might be useful to define your own function in R. And so that way, instead of calling those many lines over and over again, essentially what you do is you save those lines of code into a function, and then you just call that function. And we're going to look at examples of this. And so it ends up that this isn't difficult to do or to include inside of a script. But if we have to do, again, these calculations many times throughout the script, we don't want to have to keep on rewriting our code. And so it can get really messy. It also allows for mistakes that are easier to make, because you can imagine if you're copying, pasting the same lines of code over and over and over again, that just gives you more opportunity that maybe something didn't paste right or copy correctly. And so again, we're going to learn how to write functions. So in general, if we're writing a function, we're going to use the code that we have right here. And so this is the general format of a function, and then we're going to actually see what these look like in practice. So you'll give the function a name, and so you can think of this just like we give objects names, you can give functions names. And then to create a function, you're going to use what's called the function, and so the word function will always stay here. Inside of the parentheses, you're going to define the arguments for the function. And then between these brackets right here where I have expression, this is where you're going to put what you want to do with the arguments. So, for example, let's talk about what we mean by arguments and expression. So, we've seen the mean function in the past before. And let's say that in the mean function, I want to find the mean of the numbers 1, 2, 3. Well, in this case, the vector 1, 2, 3, that's the argument. That's the thing that's going to go inside of the function. And then thus far, we've just been providing arguments, and then in the background, the function does what we want it to do. And so in this case, in the background, this function is going to add up the numbers 1, 2, 3, and it's going to divide by 3 because there's 3 numbers here. And so that would be the expression part that we see up here. And then the final line in a function, so the one that occurs before the very last bracket, this is what we call the return value. So for example, suppose we wanted to estimate the standard deviation by taking the range divided by 4. And so this is a common technique that's used, especially when we don't have any data, but we know the range that values can take. So for example, if I needed to estimate the standard deviation of GPA, I know that a student's GPA ranges from 0 to 4 at most schools. So I could take the range, which in that case would be 0 to 4, is 4. Divide it by 4, and that would give me an estimate of standard deviation. So here I'm going to create a function, and I'm going to call it estimated SD. So just like we give objects names that have meaning, we typically want to do this with functions as well. And so my function I'm going to create is called estimate.sd. I'm going to use that function, so you'll see that I've got the word function here. Now, in order to find the estimated standard deviation, remember that the estimated standard deviation is going to always be the range divided by 4. Well, in order to know the range, really all I need to know is the minimum and the maximum value. So this function is going to take 2 arguments, minimum and maximum. And then what I wanted to do is I wanted to take the max minus the min, which is the range, and divide by 4. And then that will give me the estimated standard deviation. So first thing we're going to do is run these lines of code. And what this does is this defines the function. So notice there's no real output down here because I haven't given it any values or anything that I want it to find the estimated standard deviation of. So this is just defining the functions. And now notice now here in the global environment, we have a new section we haven't seen before. We have the function section. And we have that estimated.sd function we just created, and we see it's a function that takes 2 arguments, min and max. So now that we've created this function, we can call it just like any function that we've seen in the past. And so, for example, I could call estimated.sd, and remember my two arguments are min and max, so I could set min equal to 0 and max equal to 4. And notice now if I run this, I'll get my estimated standard deviation is 1, because 4 minus 0 divided by 4 is 1. We could change this around, and let's say maybe our minimum value is still 0, but now our maximum value is 16. And notice now we'll get an estimated standard deviation of 4. So this is always going to take the maximum minus the min divided by 4. And just like other functions that we've used in the past, we don't have to explicitly define the arguments. We can just keep them in the order that we know they are, or as they're defined. And so if I run this line of code, I will still get a 4. And so it ends up there are several extensions that we can make to functions. For example, we could return vectors, matrices, or other data types. So we've seen tables, we've seen lists. Any of those a function can return. It can even return character vectors. And so in the applied extension of our next applied extension, you're going to look at being able to do that. So for example, consider a function that takes a positive number and returns that number to the power of 0, 1, 2, and 3. So here I'm going to define my function. I'm going to call it exponent underscore fun. Often if you're reading any kind of literature about creating functions, FUN will be used as an abbreviation for function. There's other ones, FCT is often used, but just like with objects, you can call this whatever you want to. So again, I'm going to call this exponent underscore fun. That's going to be equal to, and I'm going to use that function. So I've got function. Since I want this function to take a single positive number and return it to the power of 0, 1, 2, and 3, there's only one argument, and that is going to be the number that I'm going to input. So here I'm just going to set that to be x. And then for the expression, I'm going to create a vector. And so we've seen how to create vectors many times using that C function. So notice the first element is going to be x to the 0, x to the 1, x squared, and then x cubed. So again, if I run the line of codes for this function, it pops up here now in my global environment. I can see the argument it takes is x. And we could call this function a couple different times. So maybe we want to see what this function looks like evaluated at 1. And so we can see 1 to the 0 is 1, 1 to the 1 is 1, 1 squared is 1, and 1 cubed is 1. We could do the same thing with 2. And so we get 1, 2, 4, and 8. And just like before, we could explicitly define these. So for example, we could have x equals to 1 and x equals to 2, and these will work just the same. Now the use of x here is kind of arbitrary when we define our function. I could really have this be whatever I want it to be. So for example, I could type the word apple here, and then I just have to make sure that everywhere I have x in my function, I also type the word apple. So you could almost think of this as being what's called like a dummy variable. It's really just whatever words you put there in your argument of your function, you want to make sure you use that same word in your expression. And so if we rerun the function, notice now the argument it takes is apple. And if I come down here and I try to run this with x equal to 1, notice it's going to tell me it doesn't have an argument x, it doesn't know what to do. So again, instead of x, I want to put apple, and we get exactly what we had before. So just like the name of the function is up to you, the name of what object you use as your arguments in your function is up to you as well. You just want to be consistent in whatever name you're using in your argument. Make sure you're calling that exact same name in the expression. And so as you can see from the code above, we can refer to other functions from within functions. So here I used that exponent function, and everything worked just fine. And so here's another example. So here I'm going to create a function called 10 underscore ones. And what this function is going to do is it's going to take the tens place and the ones place and create a single number. So for example, if I say that tens is 7 and ones is 5, it should return the number 75. And so to do this, we take the tens argument, multiply it by 10, and add it to the ones function. And so here we've got tens 1 with 2 arguments, 4 and 2, and hopefully we will get 42 back, and we do. And then if we have tens equal to 2 and ones equal to 7, hopefully we'll get 27 back, and we do. So you can have as many arguments as you want inside of a function, and again, you just want to make sure however you define your arguments, you use those same terms in the expression. Now you can also specify a function that has default values. So for example, maybe you want the ones to default to 5. And so that way if a user doesn't put in a value for the ones, it will just default to 5. And then if the user puts in a different value, it will use that different value. So the only difference here compared to what I did before, this time I've named the function tens ones v2 for version 2. And inside of the argument, instead of just having tens and ones, I've got tens and then I've set ones equal to 5. So notice if I call it with a single argument, what it's going to do is it's going to place 4 for the tens and 1 is going to default to 5, so we should get output 45. And you'll see that we do. This time we should get 25, and we do. But if we specify that second argument, we'll now get 27. So let's look at another example. So in all of these cases we've looked at so far, inside of our functions, notice I've just had one line of code for the expression. And it ends up by default, whatever the last line is above the brackets, that's what R is going to return. But you could write functions that have thousands of lines of code in them, and you're not restricted to just one line of code. So for example, suppose I wanted to write a function that converts Fahrenheit to Celsius. Well, if I'm going to convert Fahrenheit to Celsius, it would make sense that the argument my function should take would be the temperature in Fahrenheit. And then what it's going to do to convert it to Celsius is it's going to take that temperature, it's going to subtract off 32, and it's going to multiply by 5/9. And I'd actually like to be a little bit more explicit here, so I'm actually going to put parentheses around that fraction. So notice here, I could have, and I'm going to copy this above to show you. I could run the function like this. So this would be just like the format we've seen earlier. So I could run this. See, our new function takes tempf. And so maybe I want to see what a temperature of 55 degrees and Fahrenheit is in Celsius. Oops, I've got a typo there. And I would get that's 12.7778. Alternatively, what I could do as well and get the same result is I could take that calculation that we make inside the function, I could set it equal to an object, and then I could return that object. And so let's run this, and I'll call this one v2. Run this one. Now we have v2. But again, I'm going to call the argument the same way. And I get the exact same result. All right, let's look at another example. And so you might ask, before I go on to the next example, well, which one of these two should I use? And in this case, it doesn't matter. Either one of these are going to produce the same result. And since the last line by default is returned, either of these are perfectly fine. The return comes more handy when we've got multiple lines of code that are leading up to a result. So actually, before we go on to the other example, let's look at a version 3 and see why maybe that would be useful. So now I'm going to make version 3 of this function. But maybe what I want to do is, instead of doing these calculations all at once, I want to do them in steps. So maybe the first thing I want to do is I want to calculate the difference, and I could set the difference equal to the temperature minus 32, and then maybe my temperature C is going to be equal to the difference times 5/9. And then maybe what I want to do is I don't just want to return this piece. Maybe instead what I want to do is I want to return, I'm going to make this up on the fly here. I'm going to use the paste function, and maybe I want to say something like the temperature, oops, in Celsius, if I can spell correctly, is, not sure if this is going to work, but we're going to try it, is temp C. Alright, and so let's see what happens if we run this. We might get an error, but that's okay. So we run this. Now I will say that often if you're going to get an error, if you just run the function code like this, you're not likely to get the error. So often what you'll really want to do is troubleshoot the code that you have inside of here and then run the function. So let's actually do that. So in order to troubleshoot here, I'm going to go ahead and just set temp F to be equal to some temperature. So let's say 55. So we see that here. And so I want to check first this line of code. And I see that difference gave me what I would want it to, so I feel good with that. I see temp C, that gave me what I want it to, so that looks good. Now I can't run the return, but what I can do is see if this paste is giving me what I want. Okay, so temp C is not found. So I'm like, okay, so something went wrong there. And I noticed that I used a capital C, so let's fix that. And now let's run this piece. Okay, temperature in Celsius is this. Whew, that's a lot of decimal places, so maybe let's see if we can round this. And actually, I'm not going to round it here. Let's round it up here instead. And let's just round that difference. So let's run that again. I see the temp C is rounded up to 13. I might want to change those decimal places. Okay, that looks good. So now let's rerun our function. Let's call version 3 and see what we get. And now we got a nice return. And so again, depending on how complex your functions are, or really whether or not you're going to want to use the return, many times you don't have to. All right, let's look at another example here. So let's look at some that might actually be useful while you're working with data. So you might want to create a function that's called mean centered. So maybe you want to go through and center all of your observations in your data set. So you're going to create a mean centered function. And so mean centered is going to take an argument that's going to be a data set, or a vector in this case. And then it's going to create a new data, which is going to be equal to the original data minus the mean of data, and we're going to return it. So let's see what this would look like. I'm going to create some example data here. So the first 5 observations are 0, and the second 5 are 10. So it should be pretty easy to see the mean of this data set is 5. So what I should end up after I run my function is 0 minus 5 is going to be -5 for the first 5 observations, and 10 minus 5 is 5 for the last 5 observations. And we get exactly what we would expect. So again, we've primarily been looking at functions that are just one line, but you can have lots and lots of lines. So here's a little bit more complicated function for us to look at. So let's talk through what this is going to do. So analyze is going to be a function, and the argument it's going to take is going to be a file name. So the first thing it's going to do is it's going to create a data set. It's going to use the read.csv, it's going to read in that file. So notice the argument here is file name, and this is where the argument appears. So this function will work with many different files. You just have to change the file name. Then once that data set's created, it's going to go through, it's going to find the average day inflammation that deals with this particular data set. It's going to use the apply function to go over the columns to find the mean of the data set. It's going to plot them. It's going to do the same thing for the maximum and the minimum. And so I've got two example data sets that are going to be available on Canvas. There's inflammation 1 and inflammation 2. So let's see what that looks like. So first I'm going to run the function. And remember, when you run the function, nothing really happens down here. It's just defining the function over here in the global environment. And then we're going to run the analyze. Now before I do this, I do need to make sure my working directory has been set, and I don't think it has. So you'll see I've got that first data set here. So I'm going to go ahead and set my working directory. And so let's run this. And this is what the first plot looks like. And notice if we go back, it did create all 3 plots for this data set. Okay. Now, one thing it did not do though is it did not return the average day, or the mean, the max, and the minimum. If we wanted to do that, we could put in a return statement down at the bottom that put all 3 of those values into a vector or a table, however it is that we want to output that. So just depending on what you want your function to do is how you'll set that up. And then just for the sake of time, I won't run this for the second one, but I do encourage you to run that as well. Now, one of the nice things that you can do is you can also save functions to call in. So just like, we've used all these different functions that R has created, you can write your own functions, save them as a file, and then call them in. And so you'll notice over here, if I look in my file from my folder, you'll notice I have a file that's called analyze.r. This is also available on Canvas. But you'll notice all this is it's an R script that contains that analyze function that you just saw a minute ago. Now, I don't have all the comments in here, but it is the same function. So what we can do is you'll see that I've got analyze over here. Let's actually detach that. Sorry, I don't think I want the detach. There we go, we removed it. So notice that's gone. So if I go back over, I can use what's called the source function. And so the source function is going to go, it's going to find that analyze.r function or file, that script. It's going to run that script, but notice if we run that script, that's going to call in that function. So if I come over here and I run this line of code, notice that my analyze function, it now reappears. And then we can call it just like we did before, and we get the exact same output. So that is kind of an introduction to functions. You've got lots of different examples there. I think the first couple times you work with functions, understanding the difference between the arguments and setting up the expressions can take a bit. So I do really recommend go through, you've got lots of examples here, go through each of those examples and compare and contrast and see how the setup is different between them and get a feel for how each of those functions are working and what it is that each of them are doing. And then you can take those functions and you play around with them, make some minor changes. Remember, you can't ever break anything in R, so make some minor changes, see what happens, and that'll really give you a good feel for how these functions are set up. All right, so the last thing we're going to look at are what are called loops. There's lots of different types of loops. We're just going to go through some basic ones here. I think the first time that people see loops, they can be kind of confusing what's happening, but after you play around with them, you see several of them, it kind of clicks, and then once it clicks, you're like, oh, okay, I see what's happening here. But do know if you've never seen loops before, it can kind of take a minute to get a good feel for what is happening. So the first thing we're going to do is I'm just going to set up an example data frame that we can play around with. So what I'm going to do is I'm going to set an object called mu and an object called sigma. I'm going to run these. And then I'm going to create a data frame where I randomly sample from this normal distribution. If you don't know what a normal distribution is, that's perfectly fine. Just know that I'm simulating some example data here. And so if I click on DF, notice I've got this example data frame that has 4 columns, A, B, C, and D, and each of those have 10 rows. So I may want to go through in a data set that I have and let's say compute the mean of each of the columns. Now, as we've seen before, I could easily go through and do this with copy and paste. So I could take the mean of data frame and call the A column, B column, C column, and D column. Okay, so there are those means. But what if I had a data set that had 100 columns? Well, of course, doing this, that would be pretty tedious. I'd have to copy and paste that 100 times. So surely there's an easier way, because we're really just repeating this process 4 times. The only difference is each time I'm looking at a different column. And so one option would be to use what's called a for loop. And so what the for loop is going to do is it's going to sequentially go through each of the columns in this case, or it could be rows or anything that you want to move through sequentially. And so a for loop starts with the word for. It's going to have 2 parentheses, and those parentheses inside of them you're going to have I, N, and then you're going to have the sequence that you want to go through. So here I have 4 columns, so I want to go from 1 to 4 in a sequence. So in other words, 1, 2, 3, and 4. And what the I does is you can think of I as moving through those numbers 1, 2, 3, and 4. So inside of here, notice that I've got the letter I right here. And so what's going to happen in this for loop is this line of code is going to be repeated 4 times. And each time, the only thing that's going to change is what I is equal to. And so the first time this line of code is run, I is going to be equal to 1. The second time it's going to be 2, then 3, then 4, and then it stops because we've ended here at 4. So what I'm going to do is I'm going to call the ith column of the data frame. I'm going to calculate the mean of it, and then I'm going to print that mean. And so notice, if we move this up, what it did was it went sequentially through the columns 1 through 4, and we get the exact same values that we did when we called the mean function 4 different times. It's just the code is a little bit more compact. And again, here with 4 columns, it isn't bad, but if you had to repeat this 100 times to do the first way, you'd have 100 lines of code. For this one, all we'd have to do is change the 4 to the number 100. This is really what's happening in the background of the apply function. So if you'll remember, what the apply function does is it gives you a way to apply the same function to either the rows or the columns of a data set. If we put the number 2 here, that tells the apply function to work over the columns. And so if you'll run this, notice again, you get the exact same values. We could also store our output, and in general, that's usually what we do when we write a loop. That print function is really just used to help us troubleshoot and to see what's happening in each iteration of the loop. So here, I'm going to create a new vector. I'm going to call it output. For right now, I'm just going to fill it with NAs, and it's going to have length 4. And what I want to do is, again, for I in 1 to 4, I want output I to be equal to the mean of the ith column. So remember, anywhere that you see I here, that's where we're going to sequentially replace that with the numbers 1 through 4. So the first element of output is going to be the mean of the first column. The second element of output is going to be equal to the mean of the second column. So if we run that loop, oh, actually I need to define my output first, so we'll run both of those. And now if we look at output, see, we get the exact same means as we did before, but now they're stored in a vector so that we can actually do stuff with them. Now I will say the use of the letter I is more convention than anything. You could replace that with whatever you want. So for example, I could use the word apple. If I run this again, the output is exactly the same. It's just you'll typically see loops are written with the letter I as being the thing that changes with each iteration, or letter J is often used as well. Now we could write that loop even more generally. So maybe I don't want to hard code it with the number 4, but instead I wanted to find the number of columns that are in the data set. So here we're going to call output 2. Again, I'm going to create a vector full of NAs, but instead of specifying that there are 4 columns, I'm telling it I want R to go tell me how many columns there are in the data frame. So here the length is going to be equal to the number of columns in the data frame. It's going to do the exact same thing that it did before, except notice now instead of having the numbers 1 through 4, I'm going to use this sequence along function. So let's see, I'm going to come down here, I've got sequence along just to see what that outputs. And so notice if I take sequence along and I give it my data frame, what it does is however many columns are in that data frame, it creates a sequence from 1 to the number of columns in that data frame. And so running this loop, again, notice we get the exact same output as before. So I've got some other examples of loops here for you to look at. So here I'm going to start A equal to 0. I'm going to have a loop that runs again from 1 to 4. And what I'm going to do here is I just want each time, I want the value of A to increase by 1. So if we run this, notice what it does. Oh, sorry, not increase by 1, but increase by I. So here we started out with A equal to 0, so when I was equal to 1, we added 1 to 0 and we get 1. When I was equal to 2, we add 2 to it, so we get 3, and so on. So loops like this are really useful if we need to count something. So for example, let's just copy and paste this here and make some changes. Instead of A, let's work with the number or the letter B. So I'm going to go ahead and replace those. But let's say instead of wanting B to increase by I, we just want B to increase by 1 each time. Well, instead of I could put 1 here. So notice in this case, I doesn't appear at all inside of the loop, and that's perfectly fine because really all we want it to do is go up by 1 each time. And so here we have a counter from 1 to 4. And notice we could change 4 to be 10, and it will count from 1 to 10. And maybe instead of counting from 1 to 10, maybe we want it to go backwards. So in that case, we could, instead of having B start at 0, maybe I want B to be equal to 10, and each time I want it to go down by 1. So here instead of plus, I could do minus. And notice it goes down. So that's one way you could go down in numbers. Another way that you could go down in numbers is instead of going from 1 to 10, we could go from 10 to 1. And then here, if we want to, since we're going down by 1, notice that we really don't even need a starting place for B. We could instead have that, B is just equal to I, would be another option here. Because I is going to count down from 10 to 1. And notice we go from 10 to 1. So either of these options, whether it be to use a minus, to go down from 10 to 1, these are going to be useful for your applied extension exercise that you're going to see in the future. For loops aren't the only types of loops. There are also what are called if-else statements and while loops. So if-else statements are useful because maybe you want one thing to happen under a certain condition, but then if another condition is present, you want something else to happen. So what you can do here is maybe we could set x equal to 5, and if x is less than 10, we want it to print that x is less than 10. On the other hand, if x is not less than 10, we want it to print x is not less than 10. So notice obviously 5 is less than 10, so it's going to print x is less than 10, whereas if we set x to 500, x is not less than 10. Here's another example. We could set value equal to 0, and while value is less than 15, we want it to print value equal to value plus 4. So here it isn't going to run through a sequence, it's going to continue until a certain condition is met. So one thing you do have to be cautious with loops, while loops in particular, is if a condition is never satisfied, you'll enter what's called an infinite loop. So for example, if I set value equal to 0, and while value is less than 0, let me start that over. If I set value equal to 0, then while value is less than 15, I want it to take value and set it equal to value times 2. Well, notice if I start value equal to 0, I'm always going to have 0 times 2, which is always going to be less than 15. And so what happens if I try to run this, notice down here in my console, I never get that right pointing arrow, because right now R is just continuously running, and it would never stop because this condition is never going to be satisfied. If you accidentally write a while loop that's never going to finish, what you do is just hit stop here, and then that will stop the infinite loop. And then one last example here, and this is more for those of you that are interested in the computer science side of things. Pre-allocating can make a really big difference in computation time. And so I have a little example here just to kind of show that. So suppose that I'm going to set n equal to 1,000,000, and then I'm going to have time 1 equal to system time. And what that's going to do is that's just going to pull the current time on my computer. I'm going to set a equal to an empty vector. And then what I'm going to do is I'm just going to run a loop here where all I'm going to do is set ai equal to 1. In other words, I'm going to create a vector of ones of length 1,000,000. But what I didn't do here when I allocated my vector was I didn't pre-allocate the length of that vector. I just set it to be an empty vector. And then I'm going to capture my system time again. So essentially what this is doing is it's seeing how long it takes to run this line of code 1,000,000 times. And then I'm going to do the exact same thing, except this time when I create the vector that's going to store the output from the loop, in other words, that vector of ones that's length 1,000,000, I'm going to pre-allocate how long it is. System time. If I'm going to do the same thing, I'm going to get my beginning system time and my end system time. So in other words, how long does it take to run this loop? Confirm that the two loops give identical answers. And then I'm going to determine the time taken for each of them. And so you'll notice, although both of them were very, very quick, notice that the first way in terms of how much longer than the second time, it took, was that 5 times as long the first way as it did the second time. And here, for this particular example, it really makes no difference because, I mean, both of them were so quick. But you can imagine if you're working with a really large data set or you're working with loops that take a long time, you know, a 5-fold difference, that can be a pretty big deal. You know, if one of them takes a day to run, that could be the difference between a day and 5 days. So pre-allocation can make things run a lot quicker. And so in the notes, we've covered the first part of iteration chapter of the book that we've been using for the course. I do recommend reading the entire chapter, especially if you see yourself, you know, working a lot with data. Working with functions and loops can really speed up your process and can make your life a lot easier, especially if you find yourself doing the same task over and over again. And then after you read that chapter in the book, I've got another useful link for you to check out here. So as always, remember, you're learning new stuff. It can be frustrating, but that's perfectly fine. You can't break R. Use your online resources. Use me to ask lots of questions. Use your classmates. It really is all about just getting in here, playing around with the code. And the more you try stuff, you'll find the more you learn. You can't really do anything wrong. You can't break anything. Just always keep that in mind. And it really is the more you struggle and the more you try stuff, you're going to learn new things. So as always, if you have any questions, let me know. I'm more than happy to do whatever I can to help.